All right. So let's go over these here real quick, guys. So for question number 1, it's one of those two-part questions that we did so many of yesterday. Okay, so we got a marathon runner in a race. During the first part of the race, he runs at a speed of 7 meters per second for 1.2 hours. In the second part of the race, he slows to 6.1 meters per second for the last 10.6 kilometers. Okay, what is the average speed of the runner? All right, if they have some givens written down, part 1, part 2, and the things that were listed in the question, the speed and the time, the speed and the distance, give them a mark. In fact, give them a mark for each part. I think that's the way I have that set up. So 1 mark for each part's givens. Okay. Now, if we're going to find average speed, we need total time and total distance. Okay, we need those two things. Well, we don't have the distance for part 1, but because we have v and t, we can find it. All right, so your next mark is for calculating the distance for part 1. So d equals v times t, and that's 30,240 meters. If they don't have the 30,240 meters, but they showed this, that's a method mark. Okay, give them the mark anyway. They knew what to do. They just didn't punch it in right. Yeah, it's fine. 30.24 kilometers. Okay, it's going to come back to bite them later. Okay, if they don't change it back to meters. But and then for part 2, okay, you get a mark because we don't have the time for part 2, but again, because we have v and d, we can find it. So a mark if they've done this step here, where they've done t equals d over v, 10,600 over 6.1, gives you 1,737.705 seconds. If they just have the 1,737, you can give them a mark. Yeah. All right. Then our last step, guys, is total distance over total time. So if they've got something that shows that operation, or they showed 40,840 over 6,057.705, something along those lines, that's a method mark for knowing they had to do total distance over total time. Okay, and 1 mark, the 5th mark for the final answer, 6.74 meters per second. They must have units on that answer. Okay, if they do not, it is wrong. Okay, an answer has to have units, otherwise we don't know what it is. Okay, so make sure you've got units on that answer. All right, questions on the first one? Okay. So, in question number 2 here, we've got the question with the Lamborghini Countach versus the Redneck Mobile. Okay, so what you have to do here, if we want to find out who's going to win the race is based on what? Time, right? It's not based on speed, it's not based on distance, because those are different for the two vehicles. It's based on who gets to point B first in the least amount of time. We don't know the time for either one of those vehicles. All right, give them a mark for their givens. Okay, so car, truck. Okay, just give them 1 mark for givens on this one. Okay. Next thing, we need to give them a mark for finding the time, okay, for the car. So 980,000 meters over 110 meters per second, okay, should give you 8,909.1 seconds. All right, so a mark for the method and a mark for the time for the car. All right, you're not going to get a mark for the method for the truck, because it's exactly the same as the method for the car. All right, I'm not going to give you two marks for the same thing. Okay, so give them a mark if they got 9,218.25 seconds for the truck. Okay, and so yeah, it's 2,000. It's d over v. Okay, same as before. All right, and okay, their final mark. Car wins. Okay, car's time less than the truck's time. Okay, so that's 1, 2, 3, 4, 5. First one was out of 7. I think I only put 5 marks on there. Oh no, I've got 6 marks on there. You know what? Let's make it out of 7. Let's give them 1 for showing the work here. For showing this addition operation. That'll make it 7. Okay. We'll be generous there. All right. In the end, if they got the right answer, they get all the marks. Okay. But yeah, you don't want to try that on a test, because if you get the answer wrong and all you wrote is the answer, you get nothing, and that sucks. Yeah, out of 7, 0. Okay, we don't want to do that. All right, so yeah, give them a mark out of, what do we got there, 12, right? Okay, so give them a mark out of 12, let them see it, put it in the box at the back. Out of 12, yeah. All right, so let's talk about graphing here. How many people have built a graph before? Sadly, yes. Okay, good. So this will be pretty much review. You're going to do it again in math. Okay, if you're not taking math right now, you've probably already done it in math if you are taking math right now. But graphing is one of those skills that is ever so important, all right, because it's a scientific tool, and we use it all the time. Like, I don't think there's a single, there's one lab in Physics 20 where you won't draw a graph. Okay? Now, does that mean you have to draw graphs by hand? Absolutely not. All right? For the first little bit, we are, just because there's some mechanical stuff we have to understand about the structure of graphs and how they work. Okay? But realistically, drawing graphs by hand is, well, it's gone the way of the dodo. It's dead. Okay? It's extinct. People just don't do it because there's better ways. Okay? How many people have ever drawn a graph on Excel before, or the Mac equivalent, whatever that is? Okay? Yeah, and it's easy. It's pretty slick. It does a lot of the really cumbersome pencil work for you. Okay? And of course, it looks a lot neater than what any of us could probably do with a pen or pencil. Well, actually pencil, because you never draw a graph in pen. Because if you screw up, you have to start over, because you can't erase it. Yeah, so we'll just go over some of the mechanics of how to make a graph and do a couple of things like slope calculations and things like that. And then we'll set to work on drawing a few and doing some practice calculations with them. And then possibly this week we will just go over, if you don't already know, how to use Excel to build graphs, because quite frankly, when we do a lab, I'd prefer you did the graphs in Excel, just so I can see them. Okay, they're a lot neater that way. Best fit lines get drawn the right way. Okay, things like that. Okay, so if you're making a graph and you're doing it by hand, okay, you acquire a piece of graph paper, a ruler, and a pencil. All right. On your unit exam, you will be required to draw a graph, and obviously you can't do that on an Excel on your unit exam. So you will need to bring a ruler and a pencil to your unit exam for this unit, which is a long way off. Don't worry about it yet. Okay, but you will need that. Okay, obviously you draw the two axes. The vertical axis is the y-axis. The horizontal axis is the x-axis. All right, so you end up with something like this. All right, this is the x and this is the y. All right, the manipulated variable always goes on. Which one? X. It always goes on the x-axis. All right. So place the manipulated variable on the horizontal axis and the responding variable on the vertical axis. Crucial. All right. If you don't do that, your slope will be inverted. Okay, and we don't want that. Okay. But most importantly, you're no longer showing us what we want to see. We want to see the effect of a change in the manipulated variable on the responding variable. All right, and if you put the responding variable on the x-axis, your graph no longer shows that. Okay, so that's why we have the manipulated variable on the x. So if I have the manipulated variable on the x responding on the y, and my line goes like this, or my points or my trend or whatever go like that, what is that telling me about the relationship between the manipulated variable and the responding variable? Okay, because on this graph it's telling me that the speed of the object decreases over time. Okay, it's telling me that as the manipulated variable increases, the responding variable decreases. What kind of a relationship is that? Starts with I. When one thing goes up, the other goes down. That's inverse. Okay, so this is an inverse relationship. All right, it's important to know the types of relationships. It's not on your notes, so you probably will want to write it down, because it's terms you're going to be asked to use, okay, in this class. So this particular graph shows an inverse relationship. Okay. Okay, what does that one show? That's showing when the manipulated variable goes up, what does the responding variable do? The responding variable goes up. Okay, that is called a linear or a direct relationship. Whoa, can't spell today. Okay, so it's a linear. Usually we use the word linear, but sometimes we use the word direct relationship. When one goes up, the other goes up. Okay, and oftentimes there's a number relationship there. Like if I double the time, then the speed also doubles. Okay, that would be a perfectly linear relationship. Questions there? Okay. Hopefully you guys are just drawing the pictures, right? Just draw the pictures kind of down here so you've got one for each one. Okay. So in this relationship, when the manipulated variable increases, so does the responding variable. But does it increase directly? No, it increases exponentially. Okay, so this is an exponential relationship. Who's your math teacher, Terry? You don't have math. I was just about to compliment your math teacher. Who was your grade 9 math teacher? Okay, Mr. McLeod. He's good. All right. So we got an exponential relationship, okay, for that. Essentially what you're seeing when something like that happens would be something like this. If I double the manipulated variable, okay, the responding variable goes up by a factor of 4. Okay, if I increase the manipulated variable by a factor of 3, the responding variable goes up by a factor of 9. All right? Everything would be squared. That would be an exponential relationship. A cubed relationship would also be exponential. Okay? Everybody follow me on that one? Yes? Okay. Okay, and the last one, and you probably won't see any like this in Science 10, but it's still important to know it. Yeah, or inversely exponential, yes. Okay? In this one, it is either negatively or inversely is what we usually say, inversely exponential. Okay? This is like the relationship between how far from the sun you get and how much gravitational pull there is. Okay, or how far from the Earth you get and how much gravitational pull there is. Okay, it's inversely exponential. If I double my distance from the center of the Earth, okay, which is where gravity essentially is coming from, I will experience 4 times less gravitational pull on myself. All right, if I increase that by 3 times, I will feel 1/9. Okay, the pull. Right, and so on and so on. So as you get further and further away, okay, you feel less and less exponentially. So, everybody follow me on that one? It's the same for brightness. Okay, as you move away, like if you just have like a candle in the dark, okay, and you're right next to it, it seems quite bright. But as you move in further and further away, okay, it gets dimmer and dimmer and dimmer to your perception because all the light is filling up, okay, a very large area. Everyone follow? Okay, so that would be an inversely exponential relationship. And again, it's probably not one we're going to see in Science 10. All right, good. When we make these graphs, one of the things that you have to always be aware of, and you have to be aware of it when you're using Excel as well, because Excel will not automatically do it for you, is that you have to have labels on each axis. And those labels must include the units. Right? So if I've got time on the x-axis, I need to not just say time, but also what am I measuring the time in? Seconds, hours, days, years? Okay, what is it? Because it kind of makes a difference. All right, people need to be able to look at the units and go, oh, okay, well, I would have thought that would be different if it was in hours, and it would be. All right, so got to remember, always include the units, okay, when you're labeling your axis. And another thing that Excel won't automatically do for you, okay, is put a title on the top. Okay, And that title needs to be more than speed versus time. People can see it is a speed versus time graph by looking at the axis. There needs to be some context there. And you can see here, time versus speed for an accelerating vehicle. Right? That would mean a lot more to somebody than time versus speed. Okay? Because time versus speed could be a car, an airplane, a three-toed sloth. Okay? We don't know. But if you don't write it on there, we could assume you had a ridiculously fast three-toed sloth or a ridiculously slow airplane. Right? We just don't know. So yeah, your title needs to explain the context of the graph. All right? Now, here's the part that when people are drawing graphs by hand, I see screwed up most often. Okay? This is the part that Excel will do for you. Okay? And it won't screw it up. And that is a scale. Right? You have to make sure that every square or every line on your graph is worth the same amount. Right? You can't have, your first two lines be worth 2 and then your next two lines be worth 10. Right? Because then your graph isn't even. Right? And it's not showing the relationship properly. You can if there's a major gap between the start and where your data actually begins. Yes. I can't remember what it's called. It's got a special name, but we almost never use it. But yeah, you can do that. You actually don't put it in your best fit line. You put it here on the axis. Right, like that to indicate, so this is 0, and then let's say that this goes right to 100, and then every line after that is worth 1. That's fine. That doesn't ruin your scale. There's an indication here that there's a break in your scale. Okay, so yeah, that's, if you do that, that's okay. That's not kind of violating that rule. Yeah. All right, so you got to make sure you pick a scale that is even, and secondly, fits on your graph. All right, because I always see this, and you're going to lose a mark for this if you do it. Okay, people are like, okay, 1, 2, 3, 4, 5, 6, 7, 8. Oh crap, I ran out of lines. Oh, that's okay. I'll just draw more. Yeah, don't draw more. You did it wrong. Okay, don't draw more lines on the graph. And it's always like 1 or 2 lines. You just know they were so frustrated that they didn't do the scale right. Okay, yeah. How do I make sure that my scale, my biggest number, will fit on my graph? You take the biggest number you have to fit on your graph, and you divide it by the number of lines you have available. And that will tell you what to make each line worth. Everybody follow? Okay, that's pretty easy. All right, so I think it says that down here. Determine a scale by dividing the largest number on your scale by the number of squares and rounding up. Crucial. That's where I always see people adding one more line, because they follow the regular rounding rules. Let's say they got, when they did this, they divided and they got 10.4. Each line was supposed to be worth 10.4, and they, well, I got to round that to 10 because it's not bigger than 5. What's the problem with that? You're going to have to add an extra line because you're going to run out of lines by the end. Each line was supposed to be worth 10.4, not 10. Right? You got to round up to 11. Well, I mean, that's not a really convenient number to use for each line, but okay, you have to round up. Okay? Now, I'm not saying you have to round up to 11. Maybe you round up to 12. Okay? Or 15 would be quite a ways, but okay, round to a number that is going to make your data fit on the graph and take up pretty much the whole space, okay, but also makes sense and is easy to use. All right, everyone follow me there? Okay, so picking a scale for your graph tends to be the place where I see people make mistakes often. Okay, so you got to choose a scale that all the points fit on the graph. The graph fills a large part. Okay, what do we mean by large part? I mean at least 80% of the available space. All right. So what I mean is your graph, okay, if you do it wrong, looks like this. And your data ends there. Okay? That didn't make effective use of the space. You wasted paper. All right? Your graph should instead look like that. Okay? Pick a scale that spreads things out. Especially if you have to do any slope calculating or y equals mx plus b or anything like that. If your graph is compacted, it gets very difficult to do any reading of the graph. Okay. All right. Okay, so they just have an example here, right? If you had your biggest number was 700 and you had 30 lines to fit it on, 700 over 30 is 23.33333. Convenient number to round up to would be 25. Okay, easy to keep. You know, it's 25, 50, 75, 100. Right? It's easy to count by, and it's quick. All right. So that's kind of what you would do, and that's what they've shown here. Okay, 25, 50, 75. Now, when you've got numbers like that, it starts to get pretty crowded when you get big numbers. Okay, over here. So what we would rather see is you can skip. You don't have to write, you know, 0, 25, 50. If you go 0, blank, 50, everybody knows that each line is still worth 25. Okay? But your axis is a lot neater. All right. Once you've got your scales built, then it's time to start plotting your points. Okay, so plot them in pencil. They say here to draw a circle around each point. Don't do that. Okay. They say that indicates that there's some uncertainty with each measurement, and it makes your points easier to see. I'm not arguing that it makes your points easier to see, and I'm not arguing that it indicates there's some uncertainty, but we don't need to do it. All right. If we're going to show that there's uncertainty, we'll put error bars on. All right, and we don't have to do that in Science 10. So we're not going to do either one. Okay. All right. Number 9 there, the point 0, 0, okay, has that special name. The point 0, 0 is called the origin. Okay. If one of your scales is not started at 0, then you will not have an origin. How often do you start a graph not at the origin? Never. Okay. You should always have the origin on there. Okay. You have the origin, and then you do what MJ was saying. You put that little squiggly thing, okay, to indicate that there's a break in the axis. But you should always have the origin on your graph. Okay. All right. Questions there for the construction building of the graph? All right, I got to erase all my doodles here from the last time. Okay, so finding the slope of a line. Super important skill, because the slope of the line tells us the numerical relationship between the manipulated variable and the responding variable. Okay, if, for example, I had a graph that showed, and this is going to be a lab that we're going to do, okay, time in seconds on the x-axis and position in meters on the y. Okay, the relationship between my points is going to be the speed at which the object is traveling. Okay, because when I find the slope of this line, the units of the slope will come out to meters per second. Okay, and that'll tell me how fast the object I'm graphing is covering distance. All right, so it gives you a numerical relationship between the two things. Okay, so quick terminology, grid lines are the lines on the graph, in case you didn't know that. Okay, grid line intersection is where the grid lines intersect with each other. Okay, crossover. All right, the x-axis, horizontal, y-axis, okay, is the vertical. Okay, best fit line, okay, is an average of the plotted points. It follows the trend of your points. Okay, so we might want to write in there, follows trend of points. Okay? That's why it is also sometimes referred to, in fact, Excel refers to it as a trend line, okay, not as a best fit line. So it follows the trend of your points. It does not, I repeat, not connect the dots. This is not grade 2. A pretty picture will not form as a result of connecting the dots on your graph. Okay? So don't connect them. You don't have to anymore. All right, so it follows the trend of your points. Once we have points plotted, okay, so if we've got these points here, okay, this is a very good best fit line, what they've drawn. Some of the points are below, some of the points are above, but the line generally follows the trend, which is upwards. Okay, does everybody follow me there? Does a best fit line necessarily have to start at the origin? No. Okay, in fact, few do. All right. For example, if my points looked like this, would a trend line starting at the origin be able to give me an accurate representation of the trend? No. Okay. So your best fit line would go something like that. Okay. Not a single point ends up on the line. Is that okay? It's absolutely okay. Most of the time, none of your points will end up on the line. Right? That's perfectly okay. That's why you have grid lines. Okay? The grid lines can let you find other points for using to calculate slope width. All right, once you have a best fit line, okay, then you need 2 points on the line in order to calculate the slope. Okay? What's the formula for slope? Rise over run. Okay, so the formula for slope is rise over run. The rise is the change in y. Okay? The triangle is delta. Delta means change in. Okay? So I have a triangle here. It's delta y. It means the change in y over the change in x. You may have seen this written in math as this: y2 minus y1 over x2 minus x1. Okay, how many people is that looking familiar to? Okay, good. Where do I get those numbers from? Right, the 2 points, not just on the graph. Where do the 2 points have to be? Not just on the graph, they have to be grid line intersections, and they have to be grid line intersections that are on the best fit line. This is by far the most common mistake made in graphing. All right? People use points to calculate the slope of the line that aren't on the line. How can a point that isn't on your line tell you anything about your line? Okay? It's like asking someone who lives in Nigeria what the weather's like in Canada. Okay? They don't know. They've never been here, most likely. Okay? You guys follow me there? The points you pick have to be on the line. So here's your best fit line. Okay? We go back to this picture here. This is our best fit line. Okay? We need to find places where that line goes through a grid intersection. Okay? And that's what you can see right here. Right? The reason we want to use grid intersections is because we can follow them all the way across to the y-axis and find out the value, and all the way down to the x-axis and find out the value. All right? So let's say this was our second point. This value would be y2. This value down here would be x2. All right? Would it be a good idea to circle the points you use for your slope calculation? Yes, please do. All right. Okay, and that's what they show here. Okay, so they're showing on this picture right down here at the bottom. Okay, they found their 2 grid intersections. They've circled them. Okay, so now when they go across to the y-axis, this will be y2. This will be y1. This will be x2, and this will be x1. All right, then you can plug them into the slope formula, and you're off to the races. Okay, does that make sense to everybody? How did I know this point here should go for y2 and x2? Not necessarily because it's the largest. It happens second. All right? You determine those numbers based on the x-axis, based on your manipulated variable. The one that happens first is the x1, y1 point. The one that happens second is the y2, x2 point. All right? So as an example here, let's say that I'm using those 2 spots. Okay, imagine there's grid lines on there. I'm using those 2 spots for my slope calculation. What numbers am I getting from this point down here at the bottom? Right. This here will be x2. This here will be y2. Okay? This will be x1 and y1. All right? Why? Because this happens second. Okay? That point happens second. Now, when I do that one, my slope's going to come out as what kind of a number? Negative. And that's okay. Because it's an inverse relationship. It should be negative. It should say that as this thing goes up, the other goes down. All right? That means it's going to be a negative number. All right, is that making sense to everybody? Okay, slope calculations? No, I don't want an angle. Because if someone uses, I could have two people graph this same data and use different scales. If they use different scales, their angles are different. The angle is kind of meaningless, but those two people should get very similar slopes. Even if their scales are different, their slopes are still going to be the same because it's the same data, it's the same relationship. Yeah? All right. Okay, and then, so when we're calculating the slope here, they're saying find the height of the triangle. Okay, some people like to draw the triangle, okay, when they're doing slope calculations. I even do from time to time. Okay, this side of the triangle here is the height of the triangle, and you get that by going y2 minus y1. That's the height of the triangle. So whichever way kind of makes more sense to you. Okay, and same thing here. You find the you find the width of the triangle. All right, so that's x2, okay, x1, same idea. All right, and they divide rise over run. Okay, everybody's good with that? Alicia, sorry, you're looking. Where did? This is the slope calculation part. It's just showing you. Some people do it like they're the same thing is basically what I'm saying to you. y2 minus y1 over x2 minus x1 is the same as draw the triangle and find the height of the triangle. The reason I don't teach the triangle part is because people do this. They go 1, 2, 3, 4, 5. 5 over 1, 2, 3. And they do that. Is that the slope? The slope is 133 kilometers an hour, not 5 over 4. Okay? Because you have a scale. Right? Each one of these 5 lines actually represented some other number. Okay? You can't just count the lines up and then divide the two. It's not going to give you the right answer. Right? That's why we always say do y2 minus y1, because you have actual values from your axis then, and you get the real answer. Okay? As opposed to some fraction, okay, that's essentially meaningless. All right. Okay, and like it says here, the slope often provides important information about the data being graphed. Okay, shows the relationship between x and y. Alrighty, so give me a sec here. I think I have this to hand out to you. All right, so watch carefully, guys. I want you to kind of follow along here. Do the same steps I'm going to do, because we're going to do that first set of data together there about circumference versus diameter. Okay? Now, which one of those do you suppose should go on the x-axis? Which one responds to the other? Okay, diameter is the manipulated variable here. All right? As I increase the diameter, what happens to the circumference? It increases. Okay, so we're going to put diameter on the x-axis. We're going to put circumference on the y. All right, circumference is going to be our responding variable, right, for this particular one. All right, so on my piece of graph paper, you'll have to count on yours because you've got different graph paper than mine. On my piece of graph paper, I've got 30 lines across and 37 up. All right, I need to determine my scale. Okay, first off, in fact, I can probably put my labels on before I do that. So let's put a title and labels on here. So how circles grow. Circumference versus, I don't have enough room here, so I'm abbreviating. Obviously, you never abbreviate on a title. Okay. How circles grow. Circumference versus diameter. See, it's got a context. All right. Now, we've said already that circumference is going to go on the y-axis. All right. So circumference, and that's going to be in centimeters, right? And I'm going to have diameter, and that's also going to be in centimeters. Okay, my next thing is figure out my scales. The biggest diameter I have is 7.4 centimeters. I've got 30 lines on which to fit that. All right, so for my x scale, I'm going to go 7.4 over 30. Okay, so it says each line should be worth 0.246. Logically, I should round to 0.25. Right? Would that make sense? Make each line worth 1/4 of a centimeter, 0.25. Right? That'll fit nicely. It's easy to count by. right? 0.25, 0.5, 0.75. Everybody got me? Okay, so I'm going to round up to a logical number. Always rounding up. So on my scale here, I'm not going to draw 0.25 on every line. Drawing on every other line will probably even look a little bit crowded by the time I get finished here. All right, so here's 0. All right, I'm actually just going to go every fourth line and just make them whole numbers. 2, okay, 3, 4, 5, 6, 7, and the last one is 7.5. Perfect. Okay, it's going to fit on there great. Got to do the same thing for the y-axis. My biggest number is 23.1, okay, and I have 37 lines up. All right, 0.62. Yeah, it's not a great number to work with, okay. What could I logically round to? 0.7? Okay, right? If I round to 0.7, I'm still going to use up 80% of my graph. Would you agree? How do I tell? How can I tell if what I round to will use up 80% of my graph? Here's how you do it. Take this number, divide it by what you're going to round to. Comes out to more than 80. I'm golden. Okay, everybody follow me there? Yeah. Okay, so that can work. I'll make each line worth 0.7. It's not terribly easy to count by, okay, but it'll work. So I'm just going to go every second line here. So 1.4, 2.8, okay, 4.2, 5.6, 70, 7.0. 8.4, 9.8, sorry, 11.2. What am I doing there? And 12.6, yeah, and then this will be 14, and then I won't be able to draw on this one, but that would be 16 or 15.4, and then 16.8, and 18.2, 19.6, 21. 25, 2. All right, so will it fit on there? Okay, my biggest number is 23.1. I go up to 16. Oh, sorry. After 14 there should be 15.4, and then there's, yeah, 18.2. Sorry, I had to get small because I had my label in the way there. All right, now I've got my scale on there. Now I can plot my points. All right, so my first point is a diameter of 1.8 centimeters and a circumference of 5.6. Okay, so diameter is 1.8, so this is 1.75 and 5.6. Okay, well, 5.6 is a line, so that's great, but I do have to estimate where 1.8 is. Something like that. Okay, and then my next one is 2.8 and 8.9. Okay, something like that. 3.2 and 10.2. Okay, 4.4 and 13.8. Okay, 6.6 and 20.6. And 7.4 and 23.1. Okay, so obviously there's some estimation in where you put those points. There always is. Okay, that's why they say to put a circle around. That's why we would put error bars around if we were doing error bars. All right, but now I've got my points plotted. Now what do I need? I need best fit line. Okay, now best fit line cannot be drawn freehand. Okay, it must be drawn with a ruler or let Excel do it. Okay, if you're doing it that way. So I can cheat because I have a line tool. I don't need a ruler on here, which is good because you can't actually put a ruler on here and draw because it thinks the ruler is what you're trying to draw with. It makes an awful mess. Found that out the first time I tried it. Okay. All right, now I am going to start my best fit line at the origin for this one. All right, why is that a good idea for this graph? Well, because it's linear and because I'm pretty sure that a circle with a diameter of 0 also has a circumference of 0. I'm pretty sure about that anyway. Okay, so I'm going to start down here at 0. I'm going to draw a best fit line, okay, that follows my points. Right? Lo and behold, all my points end up on the line, or pretty much all of them. Okay, some of them are a little bit off the line. That's okay. This is one of those rare cases where, because this relationship is absolutely perfectly linear, okay, your points do all end up on the line. Because what's the relationship between diameter and circumference? Pi. What do you suppose the slope of this line should be? Pi. Yeah. Okay. Should be. We'll find out. The last time I did this, I got 3.13. I'm just that good. All right. So we need to find two grid intersections with which to calculate our slope. All right. That looks like a pretty good one right there. And that looks like a pretty good one right there. All right. I'm going to use those 2 points. You can find points on your graph, okay, that work for you. All right, and I'm just going to go across and get my y2 value, okay, my x2 value, my y1 value, and my my y1 and x1. All right, so these were 0.25, so I'm looking at slope being this. Okay, y2 is 15.4 minus this will be 7.7. Okay, and over x, 4.75 minus 2.5. All right, so that's going to be my slope calculation. Those are the values for my 2 points. Everyone follow me there? Terry? Where do I decide? Well, I found grid intersections on my line. I follow that, wherever that grid intersection is, I follow the line down to the x-axis. That's my x value. Okay, and I follow it across to the y, right? That is on your line, yes, that your best fit line passes through. Yeah. All right, so when we do that, okay, and we'll just punch that in. So, okay, 15.4 minus 7.7, okay, is 7.7. Yeah, okay. Divided by 4.75 minus 2.5. All right, well, I'm not as close as I have been in the past, okay, but it's reasonably close, right? 3.42 instead of 3.14. All right, so it's reasonably close. Everybody with me there? Okay, so we got a slope of 3.4. I would say that that's probably on the high range of acceptable. I'm not really impressed with myself, right, on that one. What are the units for that slope? It's a trick question. These are in centimeters, and these are in centimeters. What's centimeters divided by centimeters? 1. There are no units for pi. Pi has no units. Okay? You always divide the units as well when you're calculating slope. If this was in meters and this was in seconds, the units would be meters per second. Okay? But centimeters over centimeters is nothing. Alrighty? Is that making sense to everybody? Okay. Bell's just about to go here. For tomorrow, please bring some graph paper, because that stuff I gave you sucks. And I do that on purpose to discourage you from mooching it off me. Alrighty? Okay, we'll see you guys tomorrow. You too.